So today we'll discuss about the friction in the journal bearing. Okay, uh, so you can see we have a schematic of a journal inside a bearing. The shaft is known as essentially journal. Here you can see, and this part, the outer portion is the bearing, and all the mechanics involved are presented in this figure B. Here you can see. Okay, so basically this journal bearing can write that journal bearing forms a turning pair. Okay, we can see in figure A. Okay, the outer element, of the pair of the turning pair is called bearing, and the inner portion, that is your shaft, which fit which fits in the bearing is called journal. Journal. Okay. So in the figure here, in figure A, you can see this part is the journal, or we call it this as shaft. Okay, and it's this one fits inside the bearing. Okay. Now R is the radius of the shaft, W is the load that it bears. Okay, and Rn is the normal reaction offered by the bearing because of this load W. You can see. Okay, now the journal having lesser diameter compared to the compared bearing in order to have in order to have free rotation in the bearing. Okay, when the bearing is not lubricated, when the bearing is not lubricated, and the journal is at static position, That means not rotating the load W on journal and normal reaction at point A, that is your R subscript N, pass through the center. So here we can see it is at the static position. So the load acting in the shaft, okay, this and the normal reaction offered by the bearing pass through the center, okay, because it is at the static position. Okay, the bearing is not lubricated at this instant. So when at the second instant, you can say when the bearing is lubricated, when the bearing is lubricated and shaft is rotating, say in okay, clockwise direction, the lubricant form a thin layer and the point of pressure the point of pressure shifts from point A to point B. Okay, so here in the second figure we can see here, let me change the color. Now the point of pressure shifts to this point B. Okay, and we know the normal reaction should be normal to the surface. So now Rn is acting at an angle phi with the vertical. Okay, so this angle is phi and so as this. Okay, now if you extend, let me write, then I'll explain you. So point B. Okay, now let phi is the angle between R, which is the resultant of normal reaction Rn, and F, okay, force of friction, okay, and mu is the coefficient of friction and T is the frictional torque. Frictional torque in Newton meter in Newton meter, and small r is the radius of shaft in meter. Radius of shaft in meter. Then here in the figure we can see this R is the resultant of this Rn, that is the normal reaction, and force of friction, that is mu Rn, and the angle between R and Rn is phi. Okay, and point of contact has been shifted from point A to this point B. W is the load acting, and small r is the radius. Okay, this is the radius of shaft, or you can say of the journal, and the direction of rotation is clockwise. Okay, you can see here. So in this case we can write that for uniform motion, the resultant of the resultant on shaft, resultant force acting on shaft should be equal to 0. That means we can say this R should be equal to W. Okay. Now we have this frictional torque T should be equal to the load into the distance OC. Okay, OC is the distance, this one, from this point to this. This is OC, because now the point is shifted to B. So if you extend B, it will touch this central axis at point C, and the load applied W multiply with this normal distance to W is OC, will give you the frictional torque. Okay, now from the geometry we can see that this OC, okay, is equal to OB sine phi, you can say. Okay, this one is OB, from O to B. OB sine phi is OC. So now instead of this OC, we can write that W into OB sine phi. Okay, and what is OB? OB is the radius of the shaft. So it will be W dot R sine phi. Let this be equation 1. Okay, now we can write as phi is very small, substituting sine phi equal to tan phi, we have this T, frictional torque, can be represented as W dot R tan phi. Okay, or in short, we can represent this term tan phi as mu. So it will be mu W R. Okay, so our T is mu W R. Let's say this is equation 2. Now the power lost in friction. Power lost in friction, this P is T dot omega, we know. So we can represent this as mu w r into omega is 2 pi n by 60. Okay. So this is power lost in friction. Let's say equation 3. So when a circle is drawn, with center at O, with center at O and radius uh, OC, which is equal to OB sin phi, then this circle is known as friction circle. Okay, so here in this second figure you can see, if you draw an imaginary circle with this OC as our radius, which is equal to OB sin phi, then this imaginary circle is called your friction circle. Okay, this is known as friction circle. So now let us solve a problem. Suppose it is given that diameter of shaft is 60. Yeah. A 60 mm diameter shaft running in bearing carries a load of 2000 Newton. Okay, and mu is given 0.03. Find the power transmitted when n is given 1440. So now we can note down the given data. So R is given 0.03 meter, W is 2000 Newton, mu coefficient of friction 0.03, n is given speed of the shaft 1440 rpm. So the torque T, as per our derivation, it is mu wr, so we can say it is 0.03 multiply with 2000 multiply with 0.03, so it will be 1.8 Newton meter. Okay, 1.8 Newton meter, and the power lost in friction will be power lost in friction P is equal to T dot omega. So you have 1.8 into 2 pi n is 1440 divided by 60. Okay, so this P, if you calculate, it will be 271.4 watt. Okay, so in this way we can solve problems related to your journal bearing. Okay, problems related to journal bearing. So this is a very simple one. Further we'll discuss few more examples on this journal bearing. Then we'll proceed for the color and color friction. Okay.